Okay, my friends, I'm going to show you something that I don't think anybody's ever seen before. Very, very few people. I've been showing this for several years now. It was from a guy in New Zealand, Dylan Carpenter. He sent me this and a bunch of other pictures. It's fabulous, showing the magnetic fields. And so I had to study a lot about the complementary metal oxide silicate. It's called CMOS, and how the photodiodes receive and amplify and filter and all that nonsense, which was good. You know, you got to understand what you're talking about, or you shouldn't be talking about it. So I've started showing this, and then I got a guy, Mason, contacted me a couple of months ago, and we've been bouncing back and forth, and I had a 2-3 hour thing with him the other day, which, whew, I'm going to show you that. But this, what is this stuff? What is that stuff doing there? What the hell is it? Explain that to me. You don't see this from anybody that says, oh, we got all these good telescope shots. No, these guys got some special quality. Well, Mason's got a 5-inch Newtonian amplifying telescope and all kinds of filtering stuff, and it's just amazing what these guys are doing on their own, because you can't do this kind of research and show these kind of things because nobody can explain them. So when you can't explain them and you're the expert, then you just don't show them. That's what I've found. I'm not the expert, so I can show anything I want. I don't have to explain it. I want to investigate it. Okay, my friends, I'm not doing this just to brag, but I will be bragging. I did this in 1970. Just after I got out of the Army, I worked on Nike Hercules missile sites, and I took a great interest in quantum. And I came out with the intermolecular forces. There's only two types, and they are dipole-dipole interactions. There's polar and nonpolar. And then I went on to describe all of the different features about it. And the transfer of energy is from light into atomic vapor. Light is atomic vapor. It is atomic, subatomic, actually. Light is subatomic vapor. Now, the other thing is light is heat. Light is energy. That's it. All that there is light is energy. Every single thing that happens is a dipole-dipole interaction, 100%. And they're all electronic. These are all things I did to prove what happens with these particles of light and these heat. And by the time I was done, I came up with the thing that everything converts to power dissipation as electric energy. All power is electric. That's all that exists, is electric power. Every force is an interaction between dipoles. 100%. All right, I'm going to tell you right now, if you're thinking about going into chemistry or molecular anything, atomic anything, you better understand this. All molecular interactions involve electrons. 100%. Even just scrubbing across the surface, you're scrubbing across electrons, and you're creating a disturbance. Now, then you have bonding, covalent bonding, ionic bonding, where molecules hold together. So they're different atoms, and they attach to each other in different ways, holding on to each other's electrons, basically. Dipoles. So let's just forget about all this, because this is the most important part here, right? Dipole-dipole interactions. That's where I work, because a Dipole Electron Flood Theory. All electrons are dipoles. They have a black side and they have a white side, or a red or green or whatever. But this is really important to understand. In essence, all molecular interactions, 100%, which means everything. Cooking, eating, running, sleeping, breathing, all molecular interactions, whether strong or weak, arise from electromagnetic forces, dipoles. Electromagnetic dipoles, involving the arrangement and behavior of electrons in and around atoms and molecules. Dipole flood. All right, now, then they're talking about all these different kinds of forces. Well, it's most important to differentiate these molecular interactions. These are big chunks bonding to each other. Those are atoms. You got to differentiate those from the nuclear forces, whereas that's what I work at. Atoms are big chunks like this, and they're made up of a zillion little particles. I work with these ones. All right, so they say you got to differentiate, because these are very weak forces. All right, now, I don't care how tightly you bond something, how strong it is, it's nowhere near as strong as the particles that are inside the dipoles. Those are the particles that really hold. So they say you have to differentiate between the nuclear and the molecular. The nuclear is much stronger and act inside the atomic nucleus, binding protons and neutrons together. That's where I work, in that range. All right, this goes back to about 2013. Fermilab found these particles in their spray of particles when they collide. We used light, but I could see they were the same particles. This one glows and has no mass to speak of, exactly as this one. And it can get bigger and smaller. You see how this one's bigger and this one's smaller? This one just has a glowy edge around it, which it does. The black one, and has all the mass. Exactly what we found. That's the photon right there. All right, this is light coming in. And the photons are, you can see them right here, just before they smash into the Venturi and explode. This was something brand new. Nobody's ever done this before. Rod Warren did this and sent me the information, what he was doing. And this is the photon right here. Here it is in its energetic state. And you see this white stuff in front here? That's this stuff here. That's getting glowy up in front of it because it's pushing into it. Anytime you push a field into another field, you get glow. This one's not getting glowy because the black is in front of it. The black is here, so the black is hitting, and that doesn't glow. This one's getting really glowing. Now, it's going to flip. Then this one will come in front. That's upspin and downspin. That's how they call it. It always spins according to the polarity of the Earth. But sometimes the glowy part is down, and sometimes it's up. In this case, the glowy part is up. That's upspin. And this is downspin. But this is one pick of that same particle, and it's spinning like this as it goes. And then it hits the Venturi. Now this is actually what's happening here. That particle is right in there. All of these things out here are starting to glow. All right, because they're pushing through. Every field that's out here has to hit this field and get the hell out of the way. So that's what causes the glow. All right, what you're seeing right here is one of these with a positive side and a negative side. Just like a bar magnet, exactly like a bar magnet. And in the nuclear range, they are so tight, you can't break them apart. The only way you can break them apart is with the atom smashers. And they smash them, and they see these separated. We could see them as a unit, but then we actually could separate them as well, which we did. So they came through here as a photon of light, an electric particle. This is nothing more than electricity, electric particle. That's the electricity. This is the mass. It's coming forward. Well, guess what? We put it through a Venturi. You see that Venturi right there? It forced that particle, which is here, pushing everybody out of the way, and it makes its wake, just like a boat, and accelerate like a rocket ship. Once it hit the Venturi, which is here, the Venturi is so tight, a little tiny slit, that the black couldn't get through because the black can't change size. That's the key, and they know this, they say that. You see how small that is? That can get through that Venturi. The black ones can't, they bounce back. So we have effectively created raw electricity on one side of the Venturi, and the black particles stay on this side. And here it is right there. That is it. And that is electrical generation for free. We didn't have to run anything hard. We put a laser into an extremely finely tuned Venturi, and we were able to spit out complete whiteness here. Now you see, let me get a better shot of this, but they say it right here, a muon neutrino attached to the electron neutrino, the black and white one. When it hits heavy water, it creates Cherenkov radiation, which is the muon goes by itself, just like this, the black ball, and the white goes into a shower, just like this. And it increases the energy potential exponentially. I don't see why we can't harvest raw electricity right there. All right, I got some really serious people involved now, so I'm not going to go too deep today, but these are the two particles that make the dipole electron, the two of them together. They're always attached, except we were able to separate them, and they could see them separated too from Fermilab. That is actually Fermilab's picture. Now, they're normally together. They hit these particles, smash them to bits. We force them into each other and then filter. Literally, it's a filter, just like a coffee filter. It lets out the white particles and the black stays back. Simple as that. But it's got to be tuned correctly. And there's just some other little bits and pieces to it. But it's not that complicated. When I saw this, I contacted Rod Warren immediately, and he was absolute fabulous. For years we worked together on this, and I could not get anybody in the physics realm to talk, because it pretty much changed everything they've been saying. And we were able to do this. Now I have other people that are getting involved, and I can see that it maybe is going to be able to be accepted, or at least looked at. If you can't teachers can't look at what somebody can present, then you got a real problem, and that's where we're at right now. You know, the crazy thing is, they know this. Like I said, this right here was from Fermilab, and these are the same particles. There's really no question about it, because we were smashing light, and we could see it coming through the Venturi. Not only that, we could see it where it's separated, and the white and the black is behind here, which is called a boson, which is a carrier. It carries the white. And I've shown atomic bomb blasts, and the white has all the burning, and it burns a house just like this smoke. Doesn't move anything. And then the black hits, knocks the house down. All of this stuff is very, very well validated now, and we're seeing nothing but dipoles in space. And these are from guys that are not associated with any astrophysics people. They're doing research on their own and finding things that are staggering. You should see the stuff that Mason sent me. Yikes. I think this is the Seven Sisters, and this was from Dylan. But you can see the dipoles. See the dark and the white? There's some dipole moments, they call them. And these are not little particles. These are gigantic. So they have the same magnetic fields as the little ones. And you get the black and the white, and it's everywhere. It's not just there. Look, here it is right here. They show the same stuff. They're showing the exact same stuff I'm showing, only not real. This is real. Whatever this is here, it's some kind of dipole. You got the black and you got the white, and they're all dipoles. You look at this. What the hell is that? What's this pyramid up there? It looks like things are going back and forth. We got an asteroid coming into our zone in a couple of days. Who knows? Who the hell knows anymore? Everything is so avoided that you don't know what's real and what isn't. See, like I said, they know. They understand this. They just won't discuss it. There's the white ball they're showing. I don't know why they came, and a black one over here, and they're all tied together with the magnetic fields. This is showing like a space picture. It's not real, obviously. It's just a drawing. But they know you got dipoles. They're sort of easing into this, and they know this has just come out recently. This was not something, I was showing this long before that. And these dipoles, and they're everywhere. And Dylan had, look at this one. Look at that. I can explain most of this stuff. I can explain the blue, I can explain the dipoles. you know, and I can explain these rippling magnetic fields. And even this one has a double magnetic field. You see that one? And then that one? Have somebody explain that to me. I think I can. I've been working at this for many, many, many years. And the only way is I got lucky when Rod was just showing these pictures on the internet. He didn't know what they were. Nobody did. But as soon as I saw, I knew exactly what it was. And he worked with me for at least 5, 6 years. And it's been 5 or 6 years since I've had any contact with him. I mean, what do? You can't do that for the rest of your life and have nothing to show for it. But he's the guy, Rod Warren from Australia. And his nephew was Dylan. Dylan sent this stuff to me. But the first stuff, the original stuff, was from Rod. And this stuff right here, because he shows this one here. That's the red electron, you know, the red photon. And then he has green ones, blue ones, and, you know, speeding them up, slowing them down. You can do anything with this stuff if you know what to do, and he did. All right, when I was studying this, I went to all the places that were supposed to be experts. This is Yale. I took a course, a literal course, and interacted with the professors and everything at the University of Geneva, way back when this was. This was 14 years ago. Now, I got interacted with this probably 12 years or so ago. It was about 12, 13 years ago that Rod and I started to get together with this, because it was the Galaxy, well, hold on. All right, Samsung Galaxy S3 came out, I think it was 2012. So that would have been 13 years ago. And this goes back 14 years. Now, this is the professor from Yale. And I interacted with my professors from the University of Geneva. I actually took the course. And I went through Coursera. You don't have to pay for this. You can do all of these, take these courses. But I wanted to do it to be able to speak to these people. And I was able to speak to the people from University of Geneva. And I think they made some changes to CERN because of showing them that the CMOS was the way to go. It didn't interrupt any of the magnetic fields. All you're doing is accepting particles that would have just gone somewhere else. Other than that, they have to put something in there to sense it or put light into it, force energy in, and it's called the observer effect. If you're looking at it, it screws everything up. Well, you're not because you're looking at it, it's because you're adding energy or withdrawing energy. We're just sitting back here accepting for the CMOS. But here's what he has to say. And this is serious because it's true. He was being true, and I applaud him for that. Here's what he says. They got a brand new class.
News is that nobody can follow it intuitively. Richard Feynman, one of the big figures in physics, used to say no one understands quantum mechanics. So in some sense the pressure is off for you guys because I don't get it and you don't get it and Feynman doesn't get it. The point is, here's my goal. Right now I am the only one who doesn't understand quantum mechanics. In about 7 days all of you will be unable to understand quantum mechanics. Then you can go back and spread your ignorance everywhere else.
What can I say? That's what he's saying. Now, that was 14 years ago. It's still the same story today. Nobody understands it, except I think I have a pretty good handle on it. I would certainly like to talk to somebody about it, but that doesn't happen. If you have something to present and it overrides the current thinking, which is, I don't know what they're thinking now, they have no idea. They just won't talk to you. That's not the way it's supposed to work. All right, what happened was, before I went to the University of Geneva, I was getting these pictures using the CMOS. So I talked to the professors and I said, we're using CMOS and we're getting these pictures. I sent them the pictures and they said, oh, that's just, it can't be. You can't get pictures from CMOS because of these high energy particles will destroy the CMOS. And I said, no, I don't think that's true. I said, well, we're using light, which is the smallest particle. CMOS is designed to see this particle. That's what its design is for, is to see this particle. All right. the big particles that they were smashing, which are these, were throwing off chunks of so huge, like blobs like this. Of course, it would destroy the CMOS. So I said, no, you have to use the light. You can't use nuclear stuff, the nuclear big particles, atoms and so forth. And then the next thing I know, they started converting over to doing that. But they did give me a hard time. They said, oh, no, you can't do that. I said, yes, you can. If you're using light, we're down here. We're down at these particles. An X particle, this is what happens. They're taking two gigantic things like this, and they're made out of a whole batch of these, but they see them as one of these, and they're going bam, and everything goes flying. Sometimes you get a chunk this big. That hits your CMOS and it's all over. Obviously, it's like throwing a hand grenade at it. But if you just hit it with one of these, it's just like normal light coming at it, only it's, a bright light, but they're designed for that. That's what these are designed for. And this goes way back, long time ago. Here's the problem. They still want to use protons and neutrons. I don't know why, because they want to get down to the particles that I just showed you, which are the dipole electrons. So this is after I went to the University of Geneva. It says Large Hadron Collider being upgraded to handle increased luminosity. Our luminosity there is no more luminosity than we're showing. It's 100% white. It necessitated upgrades to the silicon trackers. These are the CMOS, particularly the use of CMOS pixels. The sensors, especially those using high voltage, high resistivity CMOS, are being developed to withstand the harsh radiation environment and high data rates. No, it's the harsh radiation environment. It's just too big of particles smashing into it. So they're talking about the whole idea is increased luminosity. The luminosity is what is the tiniest particles. Radiation hardness. It needed to be designed to withstand the high radiation. Exactly what we talked about. Monolithic CMOS, Atlas experiment, design approaches, CMOS, readout architecture, cost reduction. It's cheaper too. In essence, the LHC upgrade to CMOS detectors involves developing new radiation hard and high-performance silicon pixel sensors using CMOS to meet the demands of the LHC. Now, everybody's talking about it. Harvard's talking about it too. This was in 2015. Now, again, I can't remember when it was I talked to him, but it was in maybe 2013, somewhere around there. I was talking to Fermi-Lab, all of them. But I couldn't get anybody to really work with me. So this Harvard's talking this way back in 2015, radiation hardening, how to harden it. They were listening, apparently. I talked to everybody. I talked to every university, MIT, all of them. Well, I didn't really talk to a lot of them. I sent information. A lot of them I never heard back from. And then it just keeps going on. CMOS, 2019, 2021. CMOS detector system development for LHC, CMOS. That's what they have to do to be able to see these particles. And the pace of working with this is very slow and very, very expensive. It doesn't need to be that way, I don't think. All right, this is a very cool shot. It's coming in this way, and that's the green photon. And it's charged up so much. You see the bottom? That's the bottom spin. Still at the bottom spin, it's going to flip. And this one will come in front and start to take the brunt of the impact, and then they spin like that. And they actually do spin. Here's what they look like coming forward. They look like this, like a wave. You've always heard wave particle. Yes, the particle is here. This is stepped way back. We're seeing all of the interaction in the air is being excited. All of those particles have fields. They're being excited by this particle because it's accelerated, not because it's just flowing through there. Normally it would flow through there and just sort of mix like this. But this is on steroids. That sucker is flying through there. And it's now just starting to accelerate. You see it? And there's the acceleration taking right off. It hits the Venturi, and it does a nuclear explosion. It's a subatomic nuclear explosion. The particles of light, this is light here. they separate, and the black stays back, and the white showers through. There's no reason we can't put it through a photodiode and to collect this with, I would say, thin transition metal, thin films, which will absorb all the different frequencies of light, whatever is being created here. Suck it down into, you just use it or whatever, you carry it around like this, like a floating ground. You don't have to be anywhere special, you just carry it around. And that's where you would harvest the energy, right here. Because right now, the black is jumping right back in. It's instantaneous. This is such a short distance you couldn't even imagine. And light is traveling pretty fast. So between this distance and this distance, they reattach. Some would call it entanglement. The black and the white are entangled here, and then they re-entangle back here. But they don't jump over, I don't think. I think there's got to be a lot of extra black laying around. That's all I can determine. So here it's coming in. That's the light, and it's being accelerated because it senses the Venturi. And that's what happens. It's just like a nozzle on a hose. It's no more advanced than that. And that particle, which is inside that wave, particle-wave duality, the particle starts to get sucked out. And right about here, this particle senses that it just hit a wall because of the reverse. You see those lines back there? You see the reverse lines? They're not supposed to be there. That's a bounce back from the Venturi. The Venturi still continues to go forward, the particles. And then they rematch with the black ones out here. Somewhere there's black ones just laying around. That's all I can determine. Because the black ones stay this side, the white ones go through. And if you tune it correctly, that's all you get is white. You get no black coming through whatsoever, and that's what we have here. But the black jumps back into it right about this spot right here. They start to reabsorb. And the only reason you can even see the black, you would never see those black. The only reason you can see them is because they're sitting on top of the white. They don't emit, they don't absorb, and they don't reflect. All they do is obstruct. And that's dark matter. That is dark matter, my friends. And they're attached to the white matter. They're a pair. And that's what's called a dipole electron. You see, this goes way back, 2013. They knew these particles existed, and they said exactly what I say. That has all the mass, and it has all the energy. The two of them combined together make a dipole electron. And that's what they call a muon electron neutrino. Well, a muon is dark matter.